Okay, let's continue with dynamic routing protocol. Okay, some of the advantages are dynamic routing protocol can be used when the network grows bigger when you are using multiple routers. Okay, and because it's more scalable compared to static routing. Okay, and it automatically adapt and reroute the traffic whenever a primary path goes down. But it can be more complex to implement because you need to know additional commands for read, for OSPF, and so on. It's less secure because the routing packets are sent across the network, and different packets may take different routes, okay, depending on the current topology, and this may pose some little problems. And finally, we will need CPU, we will need RAM and the bandwidth to calculate the route, to send the packets, and so on. So it requires additional bandwidth and CPU time, which may slow down your network. Okay, let's look at how dynamic routing protocol works. Okay, in general, when the router boot up, okay, they will try to send and receive routing update on this interface. Okay, then they will share this routing message with other routers using the same routing protocol, and using this message, okay, then they will start to build their routing table. And when there's a topology change due to a path being goes down or interface goes down, okay, then the router will advertise the change to their neighbors so that they can update their routing table. Okay, let's look in depth on how routing protocol works. Okay, we have three routers here, R1, R2, and R3. Okay, R1 is connected to two networks, 10.1 and 10.2. R2 is connected to 10.2 and 10.3, and R3 is connected to .3 and .4 directly. So when they first boot up, okay, the directly connected interface will appear in the routing table. Okay, we will examine this using RIP version 2, where the matrix, okay, they are using is hop, how many hop away. Okay, these two networks is directly connected to R1, so it's 0 hop away. Okay, similarly for R2 and R3. Okay, these are directly connected network, 0 hop away. And these are the interface that's connected to this network. Okay, so 10.1 is connected to FA00. Okay, so when they first boot up, two routes will appear on the routing table for R1, R2, and R3. Okay. The next step, they will start to exchange routing protocol. They will send and receive routing updates from their neighbors. Okay, so let's look at R1 first. Okay, R1 will send an update. Okay, R1 will send an update. And the update packet will say that I'm connected to 10.1.0.0. Okay, how many hop away? Is 0 hop away. Okay, we will send it to R2. Okay, so what will R2 do? Okay, R2, when he receives this route, okay, he will insert it into the routing table. Okay, and when you know that it's 0 hop away for R1, you'll increase the matrix to 1. It's 1 hop away. And which interface did he receive the update? He received from S000. So this should be the exit interface for this network. Okay, because you know that R1 is connected to this network. Okay, so this tells R2 whenever you receive a packet and the destination IP address is 10.1.0.0 network, he will send it out through 0000 and pass it to R1, because you know that R1 have a route to this network. Okay, next. Okay, R2. Okay, R2 will also send an update, a routing update to R1. Okay, R2 will tell R1 that I'm connected to 10.3.0.0 network. Okay, this network. I'm connected to this network, and this network is 0 hop away. You will send it to R1. Okay, and similarly, R1, when he receives the update, he will update it in the routing table. Okay, you know that now I have a route to 10.3, and I receive this route through my serial 00 interface. Okay, and I receive it from R2, who says it's 0 hop away. I increase it to 1. So this network is 1 hop away. Okay, so that's for R1. Okay, R1 send an update and R1 receive an update. Okay, now let's look at R2. Okay, R2, okay, just now we mentioned he sent an update to R1 about the 10.3 network. Okay, he also received an update from R1 about the 10.1 network. Okay, he also received an update from R1 about the 10.1 network. Okay, so let's cover this side. Okay, R2 will also send an update, okay, to R3 saying that I'm connected to 10.2.0.0 network and it's 0 hop away. You send it to R3. Okay, what will R3 do? R3 receive this update, add it to the routing table, okay, and it's connected to my serial 001 interface. I received this update from this interface, and then it's 0 hop away. When I receive it, I will increase it by 1 to be 1 hop away. Okay, next, R3 will also send an update to R2, okay, about this network. Okay, so R3 will say, I'm also connected to this network, 10.4, and 0 hop away. And same thing, this will be updated in the routing table for R2. Okay, so this is the initial exchange, the first step of exchange for R2. R2 send an update to R3 and receive an update for R3. Similarly, he send an update to R1 and receive an update from R1, and all three routers will start to update their routing table. Okay, finally, we look at R3. Okay, we already cover R3. R3 receive an update from R2 about 10.2 network and it insert it in the routing table. And you also send an update about the 10.4 network to R2 and R2 will update it in the routing table. Okay, so that's the initial exchange, the first step of exchange. Okay, but this routing table is not complete yet because R1 still do not know that this network exists, so there's no 10.4 inside the routing table for R1. And R3 also do not know that the 10.1 exists. This routing table, this route does not exist in R3 routing table, so we need another step. Okay, one more step of exchange of routing packets so that the routing table can be complete. Okay, so in the next video, we'll look at the step 2 of the routing protocol, okay, how they exchange routes so that both R1 and R3 can have the full set of routing table.